Hi, everyone. Let's go ahead and finish off um, our discussion of the cycle index polynomial. We're basically done, but I really don't want to leave some of these loose ends open in terms of talking about the Platonic solids. And then we'll start our discussion on Polya's enumeration formula, which is our ultimate goal. But just to give you an idea of where we're going in the remaining weeks in the course, we're going to spend a few lectures on the Polya enumeration formula. I will give a full, rigorous justification for why it is what it is. We'll see some nice applications of it. And I'm actually going to combine section 9.3 and 9.4 and have that be one homework set. Perfectly reasonable as one homework set. And I'll have you turn that in a week from Wednesday. That will be your last homework set that you will turn in. Okay, so that would be a week from Wednesday. So it'd be April 22nd is when that would be due. And I'll just say it's due at 11:59 p.m., week from Wednesday. So that will be the last homework set that you will turn in. All of that will be in Canvas. So if you forget, it will be brought to your cognition again in Canvas for sure. So it's hard for me to kind of leave things undone. So, I know I said you could go ahead and think about the octahedron. There's also one other Platonic solid that we didn't really discuss at length, namely the dodecahedron that's built from pentagons. So I had mentioned that there are several things that you can build from triangles, namely the tetrahedron. Okay, and you'll be happy to know that I actually solved this today. And the tetrahedron is built from, at each point, 3 triangles coming together. Yeah. But the octahedron has 4 triangles coming together at a point. And then the icosahedron has 5 triangles coming together at each point. Okay. And everything inside is regular, so they're all equilateral triangles that we're building these things from. Then we talked about the cube at length. Again, the cube is built from squares. There are 3 squares coming together at each point, and you can't do any more than that. You're done once you have created the cube. By the way, the cube is sometimes referred to as the hexahedron, okay? Just because there's 6 sides to it. So you have the tetrahedron, the hexahedron, the octahedron. There's the dodecahedron. Okay, dodecahedron, which is 12 dodec, and the icosahedron, which, when you think about that for a minute, that's 20 triangles, okay, the icosahedron. So again, we kind of justified why it was that there were 24 group elements in the octahedron, specifically because essentially what an octahedron is 4 triangles at each point, and it's going to essentially be 2 4-sided pyramids put right on top of each other. And we'll go and look at a picture of that in just a second here. But what we said was there are a total of, at each point, 4 edges coming off, and there's a total of 6 vertices. Okay, so if you fixate on one vertex and one edge coming off of that vertex, how many possible destinations are there for that vertex and that edge? Well, there are 6 possible destinations for the vertex. And once that vertex moves, there's 4 possible destinations for where that edge could go. 6 times 4 is 24. So it's a maximum for the possible number of destinations for a vertex and an edge coming off of it. But let's go look at a picture of the octahedron situation and take a look. Okay, so this is a little wiki. Actually, I'll get out of this so that you can see fully what's happening here. It's a pretty cool little thing. It's just the Platonic solids. Okay, and there's a little wiki here that has a lot of clip art and even some rotating GIFs here that are pretty interesting. Okay, so here's the tetrahedron. I think you can kind of click through these if you wanted to. I think maybe I can even zoom in on these. Okay, get out. How do I get out of this? Well, that's interesting. Maybe I have to hit back. Okay, there we go. And I can kind of click through these things like this and see what's happening. There's the cube, or the hexahedron, if you will. And here is the octahedron, okay, which is an interesting thing all by itself. So again, you see that there are 6 vertices. There are, see how many faces? 4 upstairs, 4 downstairs. See how there's kind of like these 4-sided pyramids that are put one on top of the other. And so 4 upstairs, 4 downstairs for a total of 8 triangles. That's why it's called the octahedron. How many edges do we have? Well, there's 4 going down from that top vertex, 4 going around the middle, and then 4 going up from the bottom vertex. 4, 8, 12 total edges. So 6 vertices, 12 edges, 8 faces on this thing. Okay, it might be easier to not look at a rotating version of this to get a handle on what's happening with symmetries. So let's go here. Okay, so here's a little picture of the octahedron. Okay, what's going on with this thing? We already said basically there are 24 possible destinations. Okay, so let me see if I can get in here and annotate on this a little bit. Okay, so there are 24 possible destinations for a vertex and an edge attached to that vertex. Okay, because there are 6 places that that vertex can go. And then of course, wherever that vertex goes, that edge is going to have to go attached to it. And there are 4 possible places that that edge could potentially rotate to. Okay, so 6 times 4 is equal to 24 possible symmetries, floating symmetries for this thing. Okay, and again, you know, Burnside's theorem doesn't require that we look at all possible symmetries, but if I really truly want to let this thing float in 3-dimensional space, that is kind of an interesting thing to have in hand, all of them. And there are 24 possible things. Now let's see if we can actually construct all 24 of them. Well, there are some pretty clear ones here. So for instance, if I go on an axis through a particular vertex through the middle of this thing and out the other opposite side vertex, I can rotate around that thing, okay? And that's going to generate several things, okay? So, you know, maybe I'll kind of label some of these things. Let's see, I'll label the vertex up here A. Let's say that this is, you know, B, C, D, and the back guy is E here. And let's do F at the bottom, okay? Let's go ahead and say that row A is equal to 90-degree rotation. Let's see, okay, because how many rotations would it take to get back to the beginning? Well, there are 4 things I could rotate, right? There's actually 4 rotations. So row A is basically going to be 90-degree rotation about A, okay? And it's actually an axis through A and F, okay? And of course, I also have, let's see, row A squared, okay, which is 180-degree rotation about A. And then let's see, row A cubed, that's going to be 270-degree rotation about A, yeah? So I have row A squared, row A cubed, okay? So, and that basically pairs off, right? That pairs off, so rotation about A, and let's say through F. Okay, so that automatically pairs off with F when I do these rotations. Okay, so I'm going to have rho A squared, rho A cubed. Okay, then I'm also going to have rho B squared, and rho B cubed. Okay, right? And then let's say rho C squared, and rho C cubed. Okay, so let me just kind of keep track of these. So rho B squared, rho B cubed, and then rho C squared, and then rho C cubed. Okay, so there are 9 non-trivial rotations, and of course I also have the identity, okay, which is 0-degree rotation. Let me write that up here. Here's the identity element. So I've already found 10 symmetries of this thing. Okay, what next? Well, we've played this game before. How about opposite edges, like an axis through opposite edges? For instance, like AB and DF. Can, like, once I specify a particular edge, you know what's happening. So rotation through, like if I have an axis through the midpoint of AB and through to the opposite edge, in this case, which happens to be DF. It's going to be rotation, and that's automatically going to be 180-degree rotation. Okay, so what do I have? Rho AB, okay, which is rotation by 180 degrees through what? Hopefully you can see this okay. Maybe if I minimize my face here. Okay, rotation by 180 degrees through an axis at midpoints of AB and let's see, DF. Okay, and then the similar things for the other 180-degree rotation. Again, if I compose rho AB with itself, I'm back to the beginning. All right, so let's see here. Rho BC would be another one. And what else? So rho BC would take care of rho, or that axis would go through DE as well. And let's see, what else would I have? Maybe rho CD. Okay, rho CD would be another one. So I found 10, 11, okay, so 10, 11, 12, 13 things so far, okay? Let's see, what else are we going to have? Okay, so we have our rotations through the axes at each one of these things. Let's see, let's make sure we didn't miss anything here. So through AF, okay, so that's rho A, rho B, rho C, okay? And then what did we have? Rho AB, rho BC, rho BD, okay? Do I have other, oh yeah, I think there are other edge ones as well. So AB, okay, so AB, let's see, if I do AB, that kind of gets rid of this guy down here. BC, that gets rid of this edge over here. Okay, CD, that gets rid of this edge back here, BE. Okay, but I think I have some other things too. What else do we have? Let's see, BC, CD. I think that we also have AD, rho AD. And I think we might have, so let's see, rho AD, that guy is going to be paired with this one down here. And I think we may have one more, like rho AE. Okay, so this guy right here would be paired with this guy up here. Okay, and then I think I see one more even, like rho AC. Okay, good thing we thought about that for a little bit longer. Okay, and that makes sense because we're pairing off edges here. We have a total of 12 edges total, so there should be 6 of these. And indeed, there are 1, 2, 3, 4, 5, 6 of these sitting right there. So what do we have so far? Well, we had 9, 10, 16. Okay, 16 total things going on here. Are we missing any of these? Maybe not. I think that's probably about right. Let's just make sure we didn't miss any of the vertex ones, just to be sure. We had 6 total vertices. We pair them off. So that there's 6 total vertices, we pair them off. So there's 3 total pairs of vertices, and each give rise to 3 rotations. So we have all of those axis rotations through opposite pairs of vertices also. Okay, 12 edges divided by 2 is 6 of these rotations by 180 degrees. We have them all. Okay, and what else are we going to have? Well, we also have these interesting little facial. Okay, so let's see. Maybe I'll, like pierces through right here, goes through the middle of this octahedron and pierces and kind of goes out the back of this guy, and we can rotate around those opposite facial axes. Okay, so the opposite facial axes, how many of those are there going to be? Well, it looks like there's going to be about 4 of those, aren't there? Okay. So let's see, maybe we should label those with like the actual face that they start with. Okay, so like row ABC. Okay, and then row ABC is obviously going to be paired with something in the back, the face in the back, DEF. Okay. And what else do we have here? Actually, what we can do is we can just go around one of the pyramids, and that's going to uniquely determine all of those facial rotation axes. We could just pick a triangular face on the upper part of the pyramid. So row ABC, maybe row ACD. Okay, what else? Row ADE. Okay, and then row ABE. Okay, so what do we have so far? Okay, 16 plus 4 is 20. Okay, 16 plus 4 is 20. So we need to find 4 more of these things. So what are the others? Again, we have 10, and then we have 16, and then 20. Okay, so 10 things came from rotations, vertex rotations. 6 things came from edge rotations, and these 4 that we have so far came from facial rotations. Well, the other ones are actually from the squares of these. Okay, because remember, this right here, so like row ABC, how much is this facial rotation going to be by? Well, it's going to be 120 degrees. Okay, so then if I take row ABC squared, okay, that's going to be 240 degree rotation about that facial axis. Okay, so what's the other ones that I have? Row ABC, row ACD squared, row, what is it? Okay, so row ABC, row ACD squared, row ADE squared, and row ABE squared. And that's it. That's everything that we could have possibly come up with. Okay. So, let's think about this carefully. Okay. So look, I'm gonna clean this thing up a little bit so that we can think it through together. But let me kind of clear this for a minute. Okay. So, but then I'll quickly write down the labels on the vertices of this thing, and we'll deal with. Then we'll just briefly write down the rotations, the vertex rotations, edge rotations, etc. Okay, so let's clear this real quick. Okay, so it was A, B, C, D, E, F like this. Okay, of course I had 0 degree rotation. I had rho A and rho A squared. Okay, and we had a bunch of other things that behaved similarly to those. Okay, and then what did we have? Rho AB. Okay, and in that case, there was no AB squared or rho AB squared because it was 180 degree rotation flat out. Okay, and then we had the facial rotations, rho A, B, C. Okay, rho A, B, C was facial rotation, and then we also had rho ABC squared. Okay, so what kind of a term does rho A give rise to in the cycle index polynomial? Okay, so remember that is just vertex rotation through A and the opposite vertex F. Okay, so what kind of thing does rho A give rise to? So let's see here. Rho A gives rise to a term like what? Okay, so first of all, 0 degrees, you know what that does. 0 degree is the identity, and that's just going to be a bunch of 1 cycles. So that's going to be x1 to the 6th. Okay, what about rho A? Well, rho A is, let's see here. So A and F are going to be fixed. So I'm going to have a couple of 1 cycles. Okay. And then let's see what's going to happen. Like B, C, D, and E are going to be rotating into one another. Okay. So that's going to be a 4 cycle. Okay. What about rho A squared? What's going on with that? With rho A squared? Well, that's a little bit different. All right. Rho A squared is actually going to give rise, if you think about it, that's rotation by 180 degrees about that. So B and D are going to be in a 2 cycle, and so are E and C. Okay, and of course, A and F are still fixed. So this is going to be x1 squared, but then you're going to have a couple of 2 cycles. Okay, what about rho AB? Okay, what's up with that? Well, rho AB, I mean, that just creates a whole bunch of 2 cycles, 4 to be exact. Okay, so x2, okay, A and B are going back and forth. F and D go back and forth. And then what's going to happen? Well, E and C are going to be going back and forth, and so are B and D. So that's x2 to the 4th. Okay, so you have 4 2 cycles when you do that. 4 2 cycles. Actually, hang on a second. Not 4 2 cycles. 3 2 cycles. Sorry. Okay, 3 2 cycles. Right, because what's going on? A and B go back and forth. D and F go back and forth. And E and C are going to be flipping back and forth. B and D don't go back and forth. Only D and F do when you do that. So it's x2 cubed. Okay. Now, what about rho ABC? Okay. The facial rotation. What kind of a term does that give rise to? Well, that's going to create a couple of 3 cycles, isn't it? Yeah, so it's going to be x3 squared. Okay. And similarly, I don't think that rho ABC is going to be all that, or the square of rho ABC is going to be all that different. Okay, because basically that's 240 degree rotation, which is the same as backward rotation by 120 degrees. So that's still going to create a couple of 3 cycles. Okay. So what is the cycle index polynomial going to look like for this thing? So we know what the group is. What do I have? Is there anything that's in a 4 cycle here? Sure. So we have up to, so x1, x2, x3, x4, okay, equals 1 over 24. Okay, what's going on here? Well, I have x1 to the power 6. Okay, let's think about it here. x1 squared, x4, okay, that kind of a term comes from rho A. but it also comes from row B and row C, right? Okay, so I have plus 3 x1 squared x4, okay, plus, so let's see here. So row A, row B, and row C all give us x1 squared x4, okay. What about row A squared? What about row A squared? Well, let's see here. How many of those are we going to have? Well, 3 again, right? I don't see anything else that's going to have a form quite like that. Okay, so it's going to be x1 squared, x2 squared, and there are 3 of those. Okay, and let's see here. What about the edge rotations? The edge rotations, right, which give rise to x2 cubed. Okay, how many of those did we actually have? Well, we said that we argued that there are 12 total edges, okay? 4 going down, 4 around the middle, 4 going up. And if we pair those off, there's going to be 6 of those. Okay, so plus 6 what? x2 cubes. Okay. And what is happening here? What about the facial things? Again, there's a total of 8 faces. That's why it's called an octahedron. Okay. There's a total of 8 faces. So if I divide that by 4, or by 2 to pair those things off, I get 4 of those. So it's going to be 4x3 squared. Then, of course, I have the square of those things as well. So overall, I'm going to have plus 8x3 squared. Okay, and is that everything? Let's just make sure we're not missing something here. Are we missing anything here? What do we have? We have 14, 17, 21. I feel like I am missing something here. What is it? What is it? Well, let's see. Oh, I see. It's because row A, that was 90 degrees. Row A squared was 180 degrees. We also have row A cubed. Okay, we need to deal with that as well. So what's the deal with row A cubed? Well, that's 270 degree rotation, which is like backwards rotation by 90 degrees. So that's going to have a structure similar to row A. So that's going to be x1 squared and then a 4 cycle. So there are 3 of those, which really bumps up this guy over here. Okay, so x1 squared really bumps that up to 6. There are 6 of those things. Okay. And now I think we've accounted for everything. So 7, so right, 1 plus 6 is 7, plus 3 is 10, plus 6 is 16, plus 8 is 24. We have everything right there. Okay. So that is why this thing back over here is what it is. Okay. Indeed, we have x1 to the 6th. We have 6 x1 squared x4, right? Those come from all the either 90 degree or 270 degree rotations. The 3 x1 squared x2 squareds come from 180 degree rotation on opposite vertices. The situation on opposite edges, there were 6 of those. And there you had 3 2 cycles. And then the situation on opposite faces, the reason it's 2 times 4 is because you had not only the original 120 degree rotation, but also 240 degree rotation as well. Okay, so that's where the octahedron comes from. All right, that's pretty nice. And so as not to ruin your fun, I'm going to go ahead and leave the dodecahedron alone for now. but this is a nice place for you to kind of think about what's going on with this. I will ask you about this somewhere in the future. Hint, hint. So I would definitely think about this carefully. Think about the ways in which you could color this. In the last problem we did on the octahedron, we were coloring vertices, but again, we could have been coloring edges. Okay, that would just stretch out the number of elements the permutation was operating on from 6, because it was 6 permutations, to 12 if I wanted to talk about edges, or 8 if I wanted to talk about faces. Okay, so I would definitely familiarize yourself with the dodecahedron. I will ask you something about that, and it will sort of reveal if you know what's going on here. Okay, so first of all, given what we've done with the other given what we've done with the other Platonic solids, you should be able to determine the maximum number of symmetries and then come up with that many symmetries to pull it off. Now, one thing I will mention is why in the world, okay, so to form a Platonic solid, I'm going to have at least 3 of these shapes coming together, right? 2 shapes coming together. What's that? That's not going to create a vertex. You need at least 3, okay? And these angles that are in the middle, or that are at a vertex edge interior to the regular pentagon, are 108 degrees. And so when you put them together, you end up with a peak right here. But if you tried to put another one in here, the thing is going to be sort of like inverted. It's not even going to be flat like it would be if you tried to put a 4th square in to try to extend from the cube. In this case, you can't even stick a 4th pentagon in there to try to create yet an additional Platonic solid. So that's why there's only one Platonic solid that can be made from pentagons. And if we tried to go to the realm of the hexagon, the issue there is the internal vertex angles in a hexagon are 120 degrees. So if you tried to stick 3 hexagons together, what's going to happen? Okay, well, it's going to look like this. Okay, so there's a hexagon. There's going to be another hexagon like that. Right, these are all 120 degree angles, okay? And you're gonna just end up with a flat thing. It's not even gonna be peaked. You can't get a vertex to create a Platonic solid with the hexagons. That's why, when you've seen like the honeycomb shapes before, these things stack so nicely, okay? They're flat like this, etc. Right, so that's 360 degrees right there. So you can't create any depth with that to get a vertex peak and hence create a potential Platonic solid. So once you get to 6 sides for the irregular shape, you're done. Because if you try to go 7 or larger, the situation is just going to get worse. You're already flat when you have hexagons. So that's why there are exactly 5 Platonic solids: the tetrahedron, the octahedron, the icosahedron. Those are the 3 one conform with triangles. The cube, that's the one that you can form with squares. And then you have the dodecahedron, which is the only one that you can form with pentagons. And that's it. And Plato was actually obsessed with the fact that there were these 5 things. He tried to correspond them to elements in nature and ascribed some spirituality to the fact that there were exactly 5 of these and couldn't be any more. But it's definitely an interesting fact, but certainly I don't know what kind of spiritual significance that could possibly have. But it is interesting nonetheless. All right. Back to business here. Again, please do think about the dodecahedron and all that it entails. For sure, that will be worth your while. I do regularly update the notes, so please do download those frequently just to get the latest version. I did change a lot of things in here just to make it fit more nicely on the page, and I even added some explanatory elements down here That just happened recently. And I'm constantly tweaking this last section because I don't know that the book's explanation is all that lucid. So I've been thinking about how to do that better. And I think I may have a way to do it. And I at least want to start to introduce you to what's going on with that now. So here's kind of the goal of Polya's formula. I at least want to articulate the goal and start kind of moving in the direction of where we're going to go with this. And I don't even know that I necessarily like the way that I'm doing this right now, presently in the notes. I think I have a better way to even think that through. So I'll start to try to move us in that direction. So again, the goal in Polya's formula is we want to get a generating function which not only counts the number of classes of colorings, again, we're kind of thinking about letting items float, but it also counts the number of classes of each type. Okay, so in other words, what do I mean by classes of each type? Well, for two colorings of the square, we like to know how many classes of two colorings there are with two black vertices and two white vertices, for example. Okay, or I might be interested in knowing the number of equivalence classes, and these are the number of distinct colorings that have three black and one white, for instance. Okay, and that seems like it might be pretty tricky, maybe even impossible to pull off. And I do want to just remark at this point right here, I have said that Burnside's theorem specifically is very loose in that all you need is to have a group, okay, just a group, and you need to have some number of colorings that or number of colors that you're working with, and you need to have a certain type of coloring that you're doing. So you may impose a condition like we did in the homework, this last homework, where we said we want all of the, things we're coloring to be different if they happen to be next to each other or something. Okay. Now, when we're doing the stuff with the cycle index polynomial, that kind of goes out the window. Okay, I mean, it's still true that you can have any group at all, but when we're using the cycle index polynomial, we're kind of constructing this thing, remember, we're assuming that all possible colors can be used at any vertex. So the specialized colorings go out the window, but still the stuff with the group and the number of colors goes through. But in terms of specialized colorings, that kind of goes out the window. Okay, so let me just go up here to the cycle index polynomial stuff. And let me just say, for cycle index polynomial, no more specialized restricted colorings. Okay, Burnside's theorem does allow for such a thing, but here we were assuming that we could put any color at all at any vertex, and what we did is we sort of counted, all right, well, if I'm allowed to do that, how many colorings are actually fixed by this permutation, for instance? Okay, it just starts to get more and more complicated to deal with the situation where we have these specialized and restricted colorings, like we did in that baton problem in the homework. Okay, now we could come up with something like that that would help us out and help us pull that off, but we're not going to be, we won't be looking at that specific situation. Okay, we'll just use Burnside's theorem straight up in those cases. So back to Polya's formula. We want to know how many classes of two colorings there are with some number of black vertices and some number of white vertices, for instance. Okay, and I just kind of want to talk about this in the abstract at the beginning, and then we'll get into specifics later. And like I said, I don't necessarily even fully like the way that I'm doing it down here. It is different from the book. If you read through it, you'll notice that the book and what I write below here, it is different. I think it's a little bit more lucid, but I think there is a way to even say it in a more lucid way. Okay, and that's what I'm going to be striving to do over the next couple of lectures. Okay, so I'm going to talk about this kind of in the abstract over on the whiteboard here to finish this lecture. Okay, So let's start thinking through how we might actually try to count the number of colorings of a particular type. This is in general called a pattern inventory. Okay, so the goal, okay, hang on, that's not the right color. Let's see, the goal here is to find a so-called pattern inventory for distinct colorings under G, i.e., we want to know the number of colorings that have a certain number of vertices, edges, faces, a certain number of vertices, edges, and faces of a particular color. So I may want to know that there are 3 black vertices and 2 white vertices, etc. That's what we mean by a pattern inventory for these things. Okay, so here's something that we might want to note, just to kind of get us thinking in the right direction. We're not going to go into a huge amount of depth here, but I just want to get us thinking in the right direction. So a term from the cycle index polynomial, say, let's just say it's x1 to the a1, x2 to the a2, xk to the ak. And remember, what does that mean? Well, it means I have a1 cycles of length 1, I have a2 cycles of length 2, ak cycles of length k, and you actually know the size of the permutation based on the fact that this term is even present in the cycle index polynomial. That means that 1 times a1 plus 2 times a2 plus plus k times ak is the size of the permutation. Yeah? So a term from this thing, helps to count the number of M colorings. Okay. Can we use these terms to help with a pattern inventory? Well, I wouldn't ask unless the answer is yes. The answer is yes. Okay, and this is the essence of what's going to happen. Okay, so let's go into the next page here and we'll take a peek at what's happening. So we had this term. Okay, let me write it down again. x1 to the a1, x2 to the a2, xk to the ak. All right, so this is just a generic term in the cycle index polynomial. And suppose we have 2 colors. Suppose we had 2 colors. And let's say that it's black, which we'll notate with B, and white, which we'll notate with W. Okay? Well, let's just look at look at x1 to the a1, which this means that we have a1 cycles of length 1. Okay? Now, how in the world are we going to color? How in the world are we going to color things here? Well, you know that you basically just have freedom in each one of these slots, yes? So total number of colorings, total number of 2 colorings corresponding to x1 to the a1. Again, what you have to do is, all right, okay, this thing we're trying to count the number of colorings that are actually fixed by a particular permutation. That's where this thing arose, okay? You have to put a number of colors for each one of these ones, or you have to put the number of colors for each one of these. Corresponding to this is 2 to the a1. Does that make sense? So you basically take x1 equal to 2. Each one of those 1 cycles, you just pick a color for one of those, okay? All right, so look, let's just kind of think about this for a minute. x1 to the a1, this is like x1 times x1, okay, times x1. There's a total of a1 of these, okay? So here's the question that I have. How many, okay, how many of those colorings, okay, so how many of these 2 to the a1 colorings have 0 blacks? Okay. Well, 1. I would just have to take white for each one of those 1 cycles. Okay, so 1. Okay, so that wasn't very interesting. What about 1b? Oh, by the way, so let me kind of erase this just to make sure that we have a really complete list here. 0 Bs, and okay, if I have 0 Bs, 0 blacks, I have to color each one of these 1 cycles. I don't have any choice. I have to color each one of them, yeah? They correspond to like vertices or something. I have to color each one of those. So if I have 0 Bs, then how many whites do I have? Well, A1. Okay, so the answer is 1. Okay, there's 1 of those. Okay, what about 1 Bs? That's not really good grammar, but I'll just write it anyways. 1B and A1 minus 1 Ws. Okay, well, I have a total of A1, 1 cycles. I would just have to decide which one is going to get the black, right? And it's different, okay? It's different based on where I put that black, yes? And by the way, don't worry about things that are equivalent and stuff. That's all going to be taken care of by the dividing by the size of G later on. That's all taken care of automatically by the Burnside theorem, which is undergirding the cycle index polynomial. Okay, so how many of them are going to have 1b and a1 minus 1 w's? 1b and a1 minus 1 w's. Well, I just have to decide which of these a1 distinctive 1 cycles gets the black and the other ones get the white. Okay, so that is a1. Okay, which is really just a1 choose 1. And by the way, if you think about it, 1 is just a1 choose 0. If you think about it for a minute. Okay, so what about 2 Bs and a1 minus 2 whites? Well, there I would just have to choose 2 of the cycles in which to put black and a1 minus 2 in which to put white. And basically, that's all the whites are determined by which 2 I choose for the blacks. Okay, and so that's going to be a1 choose 2. Okay, and by the way, so I could go all the way up to, you know, any number of B's. let's just say, J B's and A1 minus J whites, well, it's going to be A1 choose J, okay? And incidentally, and this is not an accident, and this is kind of the way that things are going to go. A1 choose 0, is that not just the coefficient of what? That's the coefficient of b to the 0, w, hang on, made a little typo here. Okay, b to the 0, w to the a1 of what? Of the binomial b plus w raised to the a1. Okay, if you applied the binomial theorem, a1 choose 0 would be exactly the coefficient of b0 w to the a1. Okay, what would this be? Well, that would be the coefficient of b to the 1 w to the a1 minus 1 of the binomial expansion of b plus w to the a1. Okay, because remember, let me just kind of write this over here for your convenience. Okay, think about it for a minute. If I take b plus w and I raise it to the a1, that's going to be a1 choose 0, b to the 0, w to the a1, plus a1 choose 1, b to the 1, w to the a1 minus 1, plus dot, dot, dot. The generic term is going to be a1 choose j, b to the j, w to the a1 minus j, plus etc. Okay, so in general, okay, and we're going to kind of leave it at this, notice that the number of ways, okay, so like I have 2 to the a1 total colorings here. This is if I'm dealing with 2 colorings, and incidentally, this is going to extend to any number of colors later on. But if I have 2 colorings, then I can actually characterize how many of these colorings of the 1 cycles have exactly JBs, J blacks, and A1 minus J whites, okay? Okay, so in general, it's just going to be the coefficient of B to the J, W to the A1 minus J, B plus W to the A1. Okay, we use the binomial expansion, and we use that as a generating function to get that number. Notice we're taking the binomial expansion of the same thing every single time. And it turns out, and this may seem sort of murky and shrouded in mystery at this point, it turns out that that's really the key to telling us what to do to actually come up with a pattern inventory. Understanding this for the 1 cycles, turns out it gives us a penetrating insight into what to do with higher order cycles and how to generate a pattern inventory for those, and then a pattern inventory for the entire coloring itself. This is going to be an amazing theory that's going to develop here. This is just the beginning. We're going to, again, kind of slowly crank our way through this to make sure we understand every single detail of what's happening here. Okay, I just wanted to kind of whet your appetite a little bit for what's coming. Don't worry, again, if it feels a little bit murky. I promise it'll make a lot more sense eventually. Okay, I'm going to stop right here for now.